Hello, class. Good afternoon to you. Um, the last time we had our session, there was a technical problem with the sound. So the this lecture would be dedicated to the lecture, previous lecture, and the lectures will be repeated, but in a much faster pace. So this will be lectures on quantum mechanics. And again, our main reference, Introduction to Quantum Mechanics by David J. Griffiths. And this book is protected by copyright, and I recommend you to buy this book. However, most of the materials here are taken from this book, the very first edition of the book, which I have. Um, so in chapter 1, we knew about wave functions, and we knew about the Schrodinger equation also. And we knew that the wave functions are derived from the Schrodinger equation. The wave function is of this form, is a function of space and time. So in this chapter, we will show through some examples how to derive wave functions. But first, we will use the Schrodinger equation to solve or to determine the wave function by separation of variables. You know that the wave function is a function of space and time, but we can write it as product of two functions in which one of the functions is just a function of space and the other one is just a function of time. I hope you can say something if my audio is okay, or can you hear me over there? So anyway, um, we can solve the Schrodinger equation by separation of variables, and this is how we separate the function. So as we have said, the wave function is a function of space and time. We can make it as a product of two functions, where one of the functions is a function of space, and the other one is just a function of time. So here, sub psi is just equal to phi x times f of t. So then we can get the derivative with respect to time of psi as this one. So this is just with respect to time. So we cannot get the derivative of phi with respect to time because this is just a function of x, or a function of space. So our derivative will look like this. And our second derivative of psi, a second partial derivative of psi with respect to x, is equal to this one also. Since phi is only a function of space, we cannot get the derivative with respect to space of f. So going back to the Schrodinger equation, we substitute this. In the Schrodinger equation with this expression. So here it becomes this, and this expression in the Schrodinger equation will be replaced with this one here. We replace that in this term. So the Schrodinger equation now reads this one. And you can see that we only have phi f. So in this case, we can transform the Schrodinger equation into this expression by dividing phi f. We divide phi f on both sides, and each of these terms will be divided by phi f. So we can transform it to this equation. So in this case, look at the left side. The left side is only a function of time. And this one here is only a function of space. Function of time and function of space. So by some theorem in calculus, if two functions here, this one, the left side is a function of another variable, um, and also the right side is also a function of another variable, then you could set them to be equal to a constant. So in this case, we set the constant to be E for this side and also E for the other side. So in this case, you have this expression now. This one is equal to E, and this one also is now equal to E. So they are equal to a constant. We set the constant to be E. Again, you transform this. You can transform this into this expression by multiplying F on both sides and then dividing by IH bar. If you divide, this should be E over IH bar F, but if you place the I in the numerator, it becomes negative. So you have this expression. And here you can transform this by multiplying phi on each of the terms. So you will have this expression. This one is a simple differential equation. You can divide everything by f, and then you multiply by dt. You can get the derivative, the integral of df over f, and then also the other side, you have to get the integral, then you can find a solution for that. This one is also another expression, and this one is called the time-independent Schrodinger equation. Look, this is the momentum or the kinetic energy operator here, operating on phi. This is the p square over 2m, which is the kinetic energy. And v is the potential, which gives the constraint on the system. And phi is, of course, the wave function. But this time, this wave function is only a function of a space. And this is called stationary functions, meaning they do not change with time. They only change with position. So here you have two differential equations. But here it is, this is solvable if V is specified. But this one can always be solved. So we have to specify V, or we have to get the boundary conditions or the condition or the constraints of the system. So going back to equation 2.3, you just multiply both sides by dt and integrate. And divide by f. And the general solution would be this. So f would look like this. But see, here is just a constant. We can absorb this constant. We can absorb this constancy into the constant of phi to just make just one constant. So your f, since the constant here c, of course you can write c as always, but it's more convenient not to write c and just let c be absorbed by the constant in phi. So we are actually looking for phi f. We have the f already. This one is the f. This one is our f. So remember, f of t is just equal to the exponential of I e times t over h bar. H bar is the reduced Planck's constant, t is the time, e is the constant, and we have I, which is also a constant, which is just square root of -1. So now, as I've said, this one is called time independent Schrodinger equation, or we call that the TISE, time independent Schrodinger equation. And in this case, if we look at equation 2.4, this one, everything here is a function of space. The first, I mean, not everything. The first term is a function of space. Here you have a constant times the wave function, the stationary wave function, which is also a function of space. It would be easier to work if this is also a function of space. Phi is a function of space. V is, of course, we set this, or we assume in most of these lectures, if we deal with stationary wave functions, meaning wave functions that are only dependent with the position, if the potential V here is just a function of space. So there is a remark here, this would be harder to work if V is a function of t as well as x, but it would be much easier if V is a function of x only. Now, what is good with the separable solutions? So you will have stationary wave functions that represents the stationary states. So the probability density does not change with time. So look at here. So if we have a stationary wave function phi x multiplied to f, because psi is a product of phi f. So this one is your f. This one is your f here. This one is your phi. So your psi is just a product of phi and f. If you square this, this means that you take the modulus of psi square. This is just equal to psi star psi, or psi star. So you will have this expression. The psi star is the conjugate of psi, and the conjugate of psi just gives you, you just have to change the I into a negative I, or the negative I into I. So in this case, this will be cancelled by this. This two will cancel. Because if you add them, that would be e to the 0. E to the 0 is equal to 1. So you will have phi star phi. And this is just the modulus of phi square. So in this case, you only have a probability density that is dependent of space, not with time anymore. So that's what's good with dealing with time independent Schrodinger equation. That gives you a wave function that is just a function of space. So for anything, We have seen this formula before, but it was psi here, but now it's just phi, phi on both sides. So anything you can put in this bracket, like the total energy, the kinetic energy, the momentum, or a combination of those things, anything. What what you put here, you should also put in between the phi to get the expectation value. So to get the expectation value of any dynamical variable, um, you just use this formula, and that will be constant in time, meaning it doesn't change with time, but it changes only with position. Also, the states are of definite total energy. Definite total energy, meaning the energy is not probabilistic or not uncertain. It is really the correct energy, or it is really uh, or the energy is quantized, or the energy is fixed at a particular state. It's not an energy that is one and becomes zero later or negative later, but it is an energy that is fixed. So in this case, in classical mechanics, we have Hamiltonian, which is just the sum of the kinetic energy and the potential energy. This one, the canonical equivalent of the Hamiltonian in classical mechanics is the Hamiltonian operator. Hamiltonian operator in quantum mechanics. Here, there's a hat in above the edge. Hamiltonian operator. And your P, of course, P is IH bar, uh, IH bar over IH bar times the partial derivative with respect to x. So if you square this, you should be able to get negative h bar square partial second order partial differential with respect to space plus v. So this is the Hamiltonian operator equivalent to the classical Hamiltonian. So we want to get, so in this case, look, if we put phi on both sides, if we put phi here, we put we multiply both sides by phi here, and of course this quantity times phi. We can put phi here and the phi here, and the phi here, and the phi also here. We we will arrive at this. Um, we will arrive at this expression. So this one, this is just uh, this expression times phi, and this is equal to E phi. So therefore, um, H bar phi is equal to E phi. This means when you operate the Hamiltonian operator on the stationary wave function, it gives you an energy of that wave function. So E. So you can cancel this. You can cancel this one. Your H hat will give you a value of E as the energy of the system. So if you get the expectation value of the total energy using the formula here, using this formula, we just put H here, and then integral, of course, this is from negative infinity to um, positive infinity. positive infinity. So you have phi star, and then you have h bar, because you have h here, and then you have phi dx, and this one is equal to e phi. So e phi, e is just a constant in the beginning. So your e can be taken out of the integral here. And so you'll be left with phi star phi. So e integral of phi squared dx. And of course, the integral of the probability density from negative infinity to positive infinity is just equal to 1. So e times 1 will just be e. So therefore, the expectation value of h, the expectation value of h is just equal to e, the constant. So this is the total energy, the operator for getting the total energy. Therefore, E is the total energy. That's why we set the constant to be E, because it's actually the total energy. So we'll now go to the normalization of phi, because as I've said, um, we have to normalize the wave function, because the probability density has to be equal to 1. So we will normalize that later. So here, you have, if you operate the total energy or the Hamiltonian operator on phi in the second order here, you can write this as this one. You can first operate hat on phi first, but this one is equal to this one, e phi. So you can take e outside because it's constant, and so you operate h hat on phi. So here is, and but this one is also e phi. So it will give you e squared phi. So here you have that. So if you get the expectation value of this is an integral. You put h hat here in between. But this one is just e squared over 5. So this is e squared integral of modulus of phi squared dx. And this is just e squared, because this one is just equal to 1. So if you get the standard deviation of h, this would just be this one. It is equal to 0. What does it mean if you have a zero spread? Zero spread meaning it the the expectation value is fixed. It doesn't vibrate, or it doesn't uh, vibrate in one point. It is really fixed. So here's a conclusion of the method. A separable solution has the property that every measurement of the total energy is certain to return the value E. Again, E is the total energy of the system in that particular state, represented by phi x. Now, that is just one solution of the Schrodinger equation, but there is a general solution, which is a linear combination of separable solutions. So, for example, you have one solution phi 1 with energy E1, phi, phi 2 with energy E2, phi 3 with energy E3, phi 4 with energy E4, and so on until n equals infinity, phi 1 would have uh, a lower energy, phi 2 would have a lower energy, or could be in different order also, no? So they have different energies. So how do you write the wave functions, the wave functions for this wave function, the space-time dependent wave function? This is your wave function 1, phi 1 times exponential of negative I E1 t over h bar. And phi 2 would be this, and so on. Phi 3 would just be psi 3, I mean, this is psi 1 xt, psi 2 xt, and psi xt, psi 3 xt would be phi 3 of x e to the I e3 t over h bar. So this is the general solution of the Schrodinger equation, the time-dependent Schrodinger equation. So the time, the TDSE, or the time-dependent Schrodinger equation, TDSE, has a property that any linear combination of solutions is also a solution. The time-dependent is actually the original Schrodinger equation. What we use to solve these stationary states is the time-independent Schrodinger equation. You can see the difference. As I could show you again, this is the time-independent Schrodinger equation. The time-dependent would be um, partial IH bar partial of psi with respect to t equals at negative h bar square over 2m partial second partial derivative of psi with respect to um, time plus v psi. So that would be the difference between stationary states and the wave function. So if you write the Schrodinger equation, the general solution of the Schrodinger equation, it would be this, where each psi represented by this one will have um, contribution. Will have a contribution. Each one will have a contribution. Uh, it could be 0, it could be 1, it could be other number, but it has its own contribution to the general solution. So how do we find Cn or C1, 2, 3, and so on? So we will show that later how, but it's just good to know that this is really the form of the general wave function. So we now go to the first example, the infinite square well. Uh, in this example, we will find the wave function of particles involved in this situation where there is a constraint. Um, the particle has experiences zero potential between 0 to A, and the potential it experiences, actually it doesn't experiences because no particle can be found there in the region less than 0. uh, the potential is infinity, meaning it cannot go through that region. And for region greater than A, it's also infinity. It looks like this. This is the situation. You can imagine classically a car just moving back and forth here. In quantum mechanics, you can imagine a very small particle bouncing back and forth here in this region only. So what can we say about this particle in this region? The particle in this region is a free particle, but it cannot go out. It's free here, but it can't go beyond the walls. So that's the condition on the particle. So if we write the time independent Schrodinger equation for that, so we write, so as I will show, between um, between the between 0 and A, the potential is equal to 0. So this one will not appear in the Schrodinger equation between 0 and A, because the function has 0 potential in this region. So our time-independent Schrodinger equation will now look like this. There's no potential. And this is inside the well. Inside the well. Outside the well, phi x is equal to 0. Why? Because we cannot find a particle. So there's no wave function that represents the particle. So inside the well, this is the Schrodinger equation. We can transform it. We can transform that into this expression where k is equal to square root of 2m square root of 2m e over h bar. M there is, of course, the mass of the particle. And h bar would just be the Planck's constant. So what should we take notice of this equation? Here, energy should be greater than 0 or 0 or greater than 0. Why? Because this will not work with negative energy, this square root here. So E less than 0 is not a suitable energy for this. So the energy would be greater than 0. Now, this differential equation is just a simple harmonic oscillator, a second order derivative. So what is the function that when you get the derivative twice will give you the same function? So here and here, it's just the simple harmonic oscillator. And the sample functions that gives you the same function would be sine and cosine. So if you get the derivative of sine twice, it gives you a negative sine. And then if you get the derivative of cosine twice, it will give you a negative cosine also. So these are the two candidates. But also there's another candidate where you can also get the same function. It's the exponential I kx also exponential of negative I kx. But we use this solution. We use this phi x because we know that a particle is bounded by some walls. If, however, the exponential e to the positive negative ikx could be used in the free particle without boundary. Here you have a boundary, so it's better. It's more convenient to work with sine and cosine. So what are the boundary conditions of the particle? What are the boundary conditions? Again, here the particle is bounded. They can only move back and forth on these walls. It's bounded here. It's bounded here. At this point, at this area, the particle is nowhere to be found because it can only be roaming around here, and also in this area. So here, phi is equal to 0, or um, here is also phi is equal to 0. But here, phi is not equal to 0. But the wave function at the walls, the wave functions at the walls here, the wave function at the walls is continuous. So at the boundary, there is a condition here. The phi x and the derivative of phi with respect to x or space should be continuous. So by continuity of phi, it requires that at the boundary, phi 0 must be equal to 0, and phi of A is also equal to 0, because beyond that, there is no particle. And at the walls also 0, because the wave functions are continuous. So this is 0. So how do you say phi is 0? Using this, you can substitute x with 0, and then you have a sine 0 plus b cosine 0. But here you have a sine 0 is everything is 0, but b cosine 0 is b. But now this is equal to 0, b, so therefore b is equal to 0. So you're left with this, only this wave function. So how about when x is equal to a? When x is equal to a, this is a sine ka. So it's either a equal to 0 or sine ka is equal to 0. That's the only two options you have to make your phi x equal to 0. But this one, this a is equal to 0, is a non-normalizable because it gives you everything to be 0. All of the wave function, the stationary wave function will be 0. So that is a trivial solution. That is non-normalizable, so we don't consider that. So you're left with no choice but to choose sine ka is equal to 0. And ka, this means that it is a multiple of pi. It's a integer multiple of pi in order for you to have a sine ka equal to 0. So this one, so ka is equal to 0 plus minus pi plus minus 2 pi plus minus 3 pi and so on. But we again do not include this because again it would be trivial. It will just be like a is equal to 0. So if ka is equal to 0, everything will be 0, and there's nothing that we can get from the there's nothing that we can get out of that wave function. So it's uh, it's just fitting to neglect k is equal to k is equal to 0. So we can let now. By the way, what is the negative solution? You can check sine negative theta is just equal to negative sine theta. So we can absorb the negative sign into the constant a here. We can absorb the the negativity of sine into a. So it's just a so we can just work with the positive integer multiple of pi. So for different for for all the values of k, pi, 2 pi, 3 pi, there is a corresponding um, there's a corresponding kn. So for k1, this is 1 times pi over a. For k2, you have 2 pi over a. For k3, you have 3 pi over a. So your kn is also, there is a leveling of the k1, 2, 3, and so on. So what does it mean? What does this mean? So E, as we can check here, E is just equal to h bar square k square over 2m. But k is equal to n pi. So therefore, our energy would have this form. So this one is our energy. So what is the lowest energy? N cannot be 0. The lowest energy would be 1 square pi square h bar square over 2ma. By the way, m the a here would be equal. A is the width of the well. The width of the well here. It's the width of the well. It's the width of the well here. And the mass of the particle is m. The mass of the particle is m. So um, if we normalize phi, we can find a. We have to normalize this phi x. So we do this as we saw in the first chapter. We do this normalization formula. So everything you put the phi inside the integral, and then integrate from negative infinity to positive infinity. So this is supposed to be negative infinity to positive infinity. So this is a square sine square kx dx. So a square sine kx square. But this one is supposed to be negative infinity to positive infinity. Um, this here is only 0 because from negative infinity to 0, is there's no function. The wave function is 0. So you can neglect that, and then you can only integrate from 0 to a, because beyond a also, from a to positive infinity, is useless because there's no wave function there. So you have this integral, and then you have a square. If you get the integral of this, it would be, there are techniques to get the integral of that. You can either add a cosine square, or you can use some identities. But then anyway, you can get the integral of this, and it will just be from with limits 0 to a. It will just be a over 2. This is just equal to 1. So your a square is equal to 2 over a. So you can now write your wave function to be of this form. Your a is square root of 2 over a sine n pi over ax. So you will have phi 1x when n is equal to 1, and 2, the ground state energy would be n is equal to 1, not n is equal to 0, because n is equal to 0 is not allowed because it will make your wave function trivial. So your 1 will be your ground state, n is equal to 2 will be your first excited state, n is equal to 3 will be your second excited state, and so on. So if you look at the the plot of this wave function, for phi 1, you only have this. This is like low energy. For phi 2, you will have this wave. So this has more energy. It is more vibration is occurring. Here, more vibration occurs there. So of course, if you go to higher energies, say 100, then you will find 100 um, curves upward. I mean, you will find 100 summits and valleys here. So in this case, you only have one summit. And then here you have one summit and a valley. Then you have two summits here, one summit, valley, summit, and so if you go to 100, then it would be many. The phi n here, the phi n, say for example, if you have n equals 5 and n is equal to 7, what would that be if you get the integral, the product of the integral, where one is a conjugate? So these stationary states for the infinite well are mutually orthogonal, meaning whenever you get the product, the dot product, this is also called dot product. The dot product of phi m and n, or this is represented by integral of phi m star, or conjugate of phi m times phi x dx. They are mutually orthogonal because this integral gives you 0 unless m is equal to n. But for m not equal to n, that is equal to 0. This is the proof. I'll just go with the proof very quickly. Um, so the integral of phi m star phi n x, this would be just equal to 2 over a. This is the square root of 2 over a times square root of 2 over a. Integral from 0 to a. Why is 0 to a? Because the well occurs from 0 to a. It's supposed to be negative infinity to positive infinity, but the well only occurs from 0 to a. So this one, sine sine m pi over ax, sine n pi over ax. So you can use some identity to convert this, and then when you integrate cosine, that's just negative sign, and here you will also have this expression. So if you evaluate this with 0 to a, then it will give you 0, because this one is an integer, this one is also an integer. The sign of an integer times pi is equal to 0. So everything will be 0. But look, um, m, it doesn't work with m is equal to n. Of course, if you expand sign, m minus n times pi, you will be able to cancel m minus n. And everything will just be equal to 1 if m is equal to n. Okay? So this one will give you either 0 or 1. But 1 is only possible when m is equal to n. So that's why you can write the integral of phi m x star phi nx dx as equal to the Kronecker delta, where the Kronecker delta is equal to 0 if m is not equal to n, and 1 if m is equal to n. By the way, for any function f of x, you can write it as a linear combination of the of the stationary wave functions. Here, this one. So your wave function has a factor square root of 2 over a, then summation cn sine n pi over ax. So this is called the Fourier series of f of x. But what is n? Well, what is cn, by the way? How do you calculate that? So you can use the Fourier trick to get the cn and uh, exploit the orthonormality. This one. You can use this one. Orthonormal means perpendicular. And what it means by orthonormal is that if you integrate wave function, the conjugate of that, this one, you have two wave functions, phi m and phi n. They are orthonormal if they follow this equation. They only give 0 if m is not equal to n, and 1 if m is equal to n. So how do we get Cn here? So we can get Cn by multiplying both sides with phi m star here. Both sides here and here, or here. So you can do this. You can, fx is summation of Cn phi n. So you can, by the way, you can interchange summation and integral. You can commute the two operations, summation and integral. So you can put integral here and summation here, or you can put the summation here or integral here. Now in this case, you're getting the sum of Cn. So you're now integrating phi m and phi n, but this one is a Kronecker delta. This one, Kronecker delta, equal to this. So summation of Cn Kronecker delta. What can you say about this? This is just 1 if m is equal to n. So this one will become Cm, because it can only be 1 other, because the rest will be 0. So m is equal to n, you will have Cm here. So Cm, the 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 constant there, you can get by doing this operation, the integral of phi m star times f of x. So how about m equals 5, m equal m minus 5, or m equals 5. So you just put c5 integral of phi 5 x f of x dx, and your phi 5 will just be phi 5x equals square root of 2 over a sine 5 pi over a times x. So that's how it's done. So finally, we can write our this is not stationary space, but time dependent wave functions already, you can write it like this. So this is your phi, and this is your f. This is negative I e t over h bar. This one, this factor, and this one is your phi. So the most general solution to the time-dependent Schrodinger equation would be equal to this. That would be equal to that one. So if you set t is equal to 0, what happens? If you set t is equal to 0, 0 here, so e to the 0 would be equal to 1, so therefore psi x0 is just this one. And to be able to determine the actual coefficients, Cn would just be, you can use the formula here. Or you can use this formula to be able to arrive at this formula. I mean, this formula to arrive here. So that's how you get the wave function for this is now the wave function of the infinite square wave. So each has an energy level. Each has an energy level. 1, 2, 3, and so on. It starts with 1 because n is equal to 0 would just give you a trivial solution, and that would be representing a non-normalizable solution. So it's not included. So we'll take a breather for 1 minute, and then we'll start with the harmonic oscillator. After harmonic oscillator, that would be the end of the session, and then we will continue the next meeting after the harmonic oscillator. There are two ways to solve the harmonic oscillator. What is a harmonic oscillator, by the way? In classical mechanics, you have a mass connected to a spring fixed at the wall. So, for example, it's hanging on the ceiling, for example, the spring and the mass system. If you disturb the mass system by pulling the spring and then releasing it, the mass will vibrate up and down. So if all frictions are disregarded, the vibration of the mass will go on forever. Or if the spring is connected on a wall and then it's on the mass is attached to a floor, I mean not attached to the spring on the wall, and then the mass is on the floor, which is also frictionless, then the mass would be vibrating back and forth continuously. And the force that's acting on the mass is equal to this. In classical mechanics, this is equal to kx, where k is called the force constant of the spring. Force constant of the spring. I think you remember this in your previous courses. But F is just also equal to mass times acceleration, which is this one. This is the acceleration, the second order derivative of position with respect to time. So the solution is for this. You divide both sides by m, and you set omega is equal to k over m. So your solution would look like this, because this is just a second order differential equation, no? And it is, of course, the harmonic oscillator, just like this. Just like this. These are just the same. The solution is like that. So how do you illustrate a harmonic oscillator? One is by spring, and also if you have a bowl that is looking like this, you put a marble, then the marble will just vibrate back and forth. Will just go back and forth uh, on a point where there is the minimum of the ball. Um, so uh, so and here, going back to the harmonic oscillator, the potential energy is given by this. The potential energy, 1/2 kx squared. This is also the same formula in classical mechanics, right? This is the potential energy of the spring stretched by an amount x. So this is the potential energy, and then this is not, of course, a free particle, because the particle is moving according to the motion of the particle is influenced by this potential. So if you expand this potential by Taylor series here, you expand this potential, you will have a Taylor series. This one. This one is, of course, a minimum in the potential. So this means that the particle will just vibrate here. This is also approximately harmonic oscillator. This one, there's also a harmonic oscillator here. Here, of course, this is an unstable point. This is an unstable point. This is also an unstable point. So the harmonic oscillator is approximately here, and the harmonic oscillator approximately occurs here, here, and of course here. So in this case, the illustration is at point x sub o. So if you expand by Taylor series, this function, this potential, you can expand this by the minimum point, setting the minimum point here, v x of o plus v prime. The v prime is the first derivative of v with respect to x, evaluated at x of o times x minus x of o, plus 1/2 v prime x of o times x minus x of o square. Here, since we're only looking at very small vibrations, then this one, x minus x of o, if the vibrations are very small, this is also very small, this quantity. So if you square this quantity, it will be much smaller. So we can neglect this. We can, no, let's see. The higher order terms here, this the x minus x of o cube would be much smaller, so you can neglect x minus x of o cube and the higher order powers. This one is just a constant here, and this one, the derivative of v with respect to x evaluated at x of o is 0, so this is also 0, everything. So what's left is this one. This is now the potential, your approximate form of the potential here. This is our approximate form of the potential. This one, if you look at, if you go back, if you look at this formula, 1/2 is there. K would be the second derivative of v with respect to x. The second derivative of v with respect to x, this one, the k, and then your x square will be this one. The difference between the equilibrium and the position, it stretches or it bounces back and forth. So this is now your describe the simple harmonic oscillation about point x of O. This is simple harmonic oscillation about the point x of O with an effective spring constant of k equal to v double prime, or the second derivative with respect to x, v double prime evaluated at x of O. Virtually any oscillatory motion in the universe is approximately simple harmonic, for as long as the amplitude of oscillation is very small. So anywhere in the universe, it's estimated to be uh, also oscillatory in oscillatory motion in behavior, for as long as the amplitude is very small. But we can write this. We can write according to this. This is just 1/2 m omega square x square. So because we have this expression, um, we can write v. We can write this. So k would just be m omega square k m omega square x square here. So the the time independent Schrodinger equation will now look like this. With your this is your v. This is our v times phi equals e of phi. So there are two different approaches to solve this Schrodinger equation. The first one would be methods of series expansion, and the other one would be ladder operators. We will uh, we will solve first this Schrodinger equation, this TISE, using ladder operators. And that would be next meeting. So I will not review what uh, what an what a harmonic oscillator is next meeting. We will go directly to solving solving the the Schrodinger equation, the time independent Schrodinger equation, and in our mole room, or in our questions, even simple questions that will help you understand the lesson. You can post pictures, and then we'll try to answer your queries as much as possible, and and that would be part of your grade also, and the computation of your grades. So see you on the next schedule that we will have. We will fix that. So that's all for this session, and I hope you understood even a little of the lecture. Thank you so much.